So this is the last lecture. This is what I hope to tell you about today. I want to very, very briefly talk about how you measure CP violation in neutrino oscillations. Then I want to spend a little bit of time talking about neutrino experiments that are not related to neutrino oscillation. And they are usually guided by two very well-defined questions, which is what are the neutrino masses? And the other ones are guided by whether the neutrino is a Dirac or a Majorana fermion. And then for the sort of the latter part of the talk, I'll talk a little bit about models. Models for new masses. So this is kind of the plan, and then we'll see how it works out. So the first thing I want to talk about very briefly, so I did introduce this formalism for neutrino oscillations very briefly, and we talked a little bit about this in the discussion as well. To make a long story short, neutrino oscillations are driven by two oscillation frequencies that are governed by the neutrino mass square differences. And then there are two of those which are linearly independent that we're very sure exist. One of them is about 10 to the minus 4 electron volts squared. The other one is about 10 to the minus 3 electron volts squared. If you put in one significant digit of a precision here, this is about 2 times 10 to the minus 3, and this is about 0.8 times 10 to the minus 4. But this is order of magnitude-wise what it is. And as I wrote down yesterday, we've also measured, we have a lot of information on the entries of the mixing matrix. And let me tell you what that information is, because it is important for appreciating a couple of things. So again, if you write down the mixing matrix square, entry of the mixing matrix squared, from the experiments that I try to describe in a lot of detail in the first lecture and a half, we have information on these numbers squared. And to be very, very concrete, if you look at neutrinos that are done with solar neutrino experiments, they effectively measure, so this is 1, 2, 3, they measure this number here, that's about a third. And we're sure that this number here is about 2/3. And we have the solar neutrino experiments measure mostly this number. Then there's another experiment which I didn't talk about, but it confirms the oscillation interpretation of the solar data. That's called the Camland experiment. This is a reactor neutrino experiment with a baseline of about 100 kilometers, which is a very crazy experiment that actually worked. And they actually measure the product of those two numbers really well. This number here, we've measured that with the Diabé experiment. That's like a few percent. So I don't know, I say 0.02, something like that, for the mixing angle squared. And that's measured by these reactor experiments. And that's also confirmed by a long baseline oscillation experiments in Fermilab, the NOVA experiment, and the T2K experiment in Japan. Then there are two other numbers here that we've measured. There's this number here, that's about a half. This comes from the atmospheric neutrino experiments. This measures how much the muon neutrinos are disappearing that are produced in the atmosphere. This has been confirmed by accelerator experiments done in Japan and in the US, and we're very, very sure that this is going on. This is mostly everything that we've been able to measure out of this matrix directly. So all of the information that we have is in these 4 numbers. We have done a little bit better. So we have a little bit of information on this number, and the error bar is really big. So this number here comes from asking yourself, what's the probability that a muon neutrino produced in the atmosphere is detected as a tau neutrino? That number is different from this one. This one measures what's the probability that a muon neutrino will disappear along the way into something else. And of course, because this number is so small, we can infer that this number here is about a half. But if we try to measure it directly, we can do it, but the error bar is sort of ridiculous. But let's say it's about a half as well. Now, lucky for us, once we've established a whole bunch of these numbers, we can fill in the rest of the numbers as well by assuming that the matrix is unitary. So by using unitarity, we can fill in what the other numbers are. And that's what I wrote down before, right? This is like a third, and a third, and this is like a sixth, and a sixth. So this is what we've done in terms of taking this idea of neutrinos have mass, and then there are 3 of them, and then trying to explain all of the data. As I try to illustrate by filling in this matrix very slowly, the data allow us to measure very precisely a small subset of this matrix. The rest of that is inferred by assuming that the matrix is unitary. And what's exciting about this is that once you make this assumption, these measurements have gotten to the point where they can be called precise. So most of the mixing angles, or most of these numbers here, are known at the under 10% level. This one, ironically, was the last one that we got to measure, but once we've seen it, actually we can measure it really well. This is known at the few percent level. This one is known maybe at the 5% level. Even more ironically, this one, which is the first one that we got to confirm experimentally directly and we were very sure was there, this is the one that has the biggest error bar by far. So 0.4 is allowed for this number, for example. So that's about like a 20% uncertainty. And of course, what I think I mentioned yesterday in the discussion, if this matrix is not unitary, we would not know what it looks like. So asking the question as to whether this is a unitary matrix, it's not something that we've been able to do very well. With one exception, which is we have a lot of information about this first row. So we know that these 3 numbers here add up to 1 at the several percent level. I'll make something up, 6% or 7%, something like that. Okay? So there's one piece of the puzzle that's not there and that you could have access to with neutrino oscillations, which is the fact that I'm plotting the elements of the matrix squared. Again, this is really bad notation, right? This does not mean U squared. It means the entries squared of the matrix itself. But there's one extra piece of information, which is a CP violating phase, just like in the CKM matrix. So the question is, what is this CP violating phase? And let me very quickly tell you how we think we're going to measure this. And I'll try to do it in a more physical way. So the channel that we concentrate on for doing most of these measurements is to try to measure as precisely as possible the probability for producing a muon neutrino and measuring that as an electron neutrino. So it's this number here. And it's very easy to understand why that's the thing that we like to measure the most. Actually, that's not the thing we like to measure the most. The thing we like to measure the most is the probability that a new mu will disappear. Because we have very good sources of muon neutrinos, and we can play with their energies a lot. So if you ask how do we produce our neutrinos, we're pretty much stuck with the stuff that was figured out 60 or 70 or 50 years ago. We can get neutrinos from nuclear reactors. That's a strong flux. That's a flux of electron antineutrinos that's very low energy. That's like 10 MeV. And as I try to emphasize, that's not a beam. That's just a box that emits neutrinos everywhere. And that means any experiment that you build only sees a tiny fraction of all the neutrinos that are emitted. And also, if you remember, these neutrino experiments rely on you letting the neutrinos propagate a long distance. That makes these experiments extra hard. And on top of that, these experiments are so low energy that the only thing you can detect are the electron neutrinos themselves. So if the electron neutrino changed into a muon neutrino, you're not able to ask the answer to that question because the energy is too low to produce a muon. So we like the muon neutrino sources. These are coming from pion decay. So you produce a bunch of pions. They have charge, so we can collimate the pion beam. The pions decay into neutrinos. We hope that all the neutrinos will keep on going in the same direction, and that gives us our neutrino beam. Again, if you've never thought about this, neutrino beam is an approximate term. If you have a picture of a beam, like say the LHC beam, which is this nice beam of particles, which is about this big, and you can't see it from there. A neutrino beam is about this big, about 100 meters away. The neutrino beam that goes, for example, from Fermilab to Minnesota, the radius of the beam is measured in kilometers. So it's a beam very, very loosely speaking. But nonetheless, that's fine. So we're very good at doing new mu beams. And of course, we have to ask what kind of energies do we need. And the problem is the oscillation phenomenon scales like L over E. We know the delta M squares. These are the numbers that we can't change. They are whatever nature told us the numbers are. So if you wanted to look for taus, for example, you must have enough energy to hit something and produce a tau. Experimentally, that's very difficult, but on top of that, you need a lot of energy. So if you wanted to have a new mu oscillating into a new tau, and you wanted to see that, you definitely have to be above tau threshold, which is a few GeV. And just being a little bit above threshold is probably not good enough, because if you're at threshold, the number of particles you get is really small. So you would like to be way above threshold. The problem is things scale like L over E. And the problem is, for a 1 GeV neutrino, if you want to see the fast oscillation, which has this delta M squared of about 10 to the minus 3, you have to be about 1,000 kilometers away. So you can quickly convince yourself that if you wanted to do an experiment at 10 GeV, you would need to be 10,000 kilometers away. And you can quickly remember that that's how big the Earth is. So if you'd like to restrict your experimental activities to the planet Earth, that's as good as it gets. You can't do any better than that. So that's why looking for tau appearance is difficult. It's intrinsically difficult from an experimental point of view. It's pragmatically very, very difficult because we live in a small planet. We could try to fix that, but that's okay. So this is a channel that we look for. The other one that we would look for is the new mu's oscillating into new mu's. And then you could ask yourself whether I could use that to look for CP violation. And the answer turns out to be no. Because the way that we look for CP violation in the neutrino sector is probably the most textbook way of looking for CP violation you can come up with. It is way better than the way you look for CP violation in the kaon sector. So I don't know if people still talk about CP violation in the kaon sector. These are the classic experiments from the 60s. It's really hard to explain how CP violation is measured in the kaon sector. So if you've ever seen that, neutrinos are way nicer. So the way that we look for CP violation in the neutrino sector is very simple. We look at a channel. So you produce a neutrino with some flavor, you measure it with a different flavor. We look at the same channel in the antineutrinos, so let me call that this. And then we ask if these numbers are the same or not. So that's the question. And if they're not the same, CP is violated, because you have particles or matter doing something different from antimatter. So that's what you're looking for. So if you were doing new mu disappearance, which is asking if the new mu's are going into something else, and you compare that with anti-new mu disappearance, those two numbers are guaranteed to be exactly the same, even if CP is violated, because of the CPT theorem. So the CPT theorem says that those two numbers are the same. Because again, the only difference is you have to run the movie backwards. But if you're starting and ending with the same thing anyway, then those two movies are the same if you turn particle into antiparticle, which means that those two probabilities are the same. So this is the one that we like to measure the most in order to try to get the CP violation. It's a challenging measurement to do, and I'll try to point out why that's the case. So this probability looks like, so I start out with a new E, which I said looks like this. So this is the part of the amplitude for doing this. I'll put a 1 here. So I'm not done yet, but this is what you start out with. So it's a UE1 times nu1 plus UE2 times nu2 plus UE3 times nu3. That's the electron neutrino. Each one of these components picks up a phase that looks like this. And then you measure this. Oh, I'm doing this the other way around. This should be mu. And then you measure this as an electron neutrino, so you project it onto the electron neutrino state. So this is the amplitude for this thing to happen. So the probability is this number here squared. Okay, so this is something that we can try to measure experimentally. It depends on the baseline and it depends on the distance. And of course, if I ask what's the probability for the antineutrinos, it looks the same, except that these pieces here get exchanged. And I should do it right, which is even better. So the question that you need to ask yourself is this number squared going to be different from this number squared? That looks like a very simple question. And if you stare at this, there's a lot of hope that this will work out. Because again, these are two different numbers. So that's good. If they were the same number, the magnitude squares would definitely be the same. So it's good for us that they're not. Okay. Now, in order for us to identify what does it take to have these two numbers be the same, I'm going to simplify this expression a little bit. So I can pull out this factor here. So this becomes delta m squared 2, 1. And this becomes delta m squared 3, 1. Okay, and clearly that doesn't change the magnitude squared of that complex number. Then I can do one last thing, which is if I pretend that the matrix really is unitary, then this thing squared, this is equal to minus UE2 star U mu 2 minus UE3 star U mu 3. Just because the matrix that I have to begin with is unitary. So that means I can replace this term by that. So if I do this, this goes here. I get this minus 1, and then I get this minus 1. Okay, so this is a number that I get, and again, for the antineutrinos, I get exactly the same thing, except that the u's are reversed with respect to one another. Now we can stare at this and we can ask whether this number squared can be different from this number here squared. So let me write it this way. Okay, and you can notice lots and lots of things. First of all, so this here is the sum of two terms. So there are two complex numbers. There's this complex number and this complex number. And one non-trivial statement I can make, which, yeah.
But you need an extra one.
Which one?
It was the sum of all of the u's is equal to 1 over.
Yeah, so I use that, and I can use that in the bottom as well.
But then you want 1 minus UU minus UU.
I use that, and that's where these minus ones came from. Or does that make sense? Because I had a UU plus UU plus UU. I make this guy into minus this one. It's to 0. I apologize. It's equal to 0. Good. Sorry. Yeah, that's exactly right. Thank you. So you notice that so first of all, if all the u's were real numbers, then those two things are exactly the same. So CP is not violated. So you need this parameter delta, which makes the entries in this matrix complex, to be non-zero, or not pi, for example. That's one restriction. The other restriction is interesting. If any one of those two components to this amplitude are 0, then you also get that this thing squared is equal to this thing squared. That's easy to see because here you would have a complex number that goes like a times b. This would be a star times b, and the magnitude of a times b is the same as the magnitude of a star times b. Is that clear? So again, if you want to have a non-zero effect, that means that both of these terms have to be non-zero. There's a lot of, this means lots of things. It means, for example, that we need all the u's to be non-zero. So if any of the elements of the matrix were 0, then you would not be able to see CP violation. In practice, it also means one other important thing, which is if this exponential here is 1, then this guy here vanishes. Or if this exponential here were 1, then this guy here would vanish. The exponential vanishes when the argument of the exponential is very small. So if the argument of the exponential is very small, this term here vanishes. And this, of course, is a small delta m squared. So that kind of tells you that you need a long baseline. You need L to be big enough so that you're sensitive to the fact that this exponential here is not 0. Okay? So this gives you all of the conditions that you need in order to measure CP violation, and it tells you that you need to look for an appearance probability, and this is the most fruitful one that we can think of, and you need a very long baseline experiment so that you can see this. And in reality, the experiments that we come up with, these terms here end up being hierarchical, which is interesting. So normally when you have a sane experiment, this term will be bigger than this one. And the way that you set up the experiment is that you would like, so this term squared is the biggest, followed by the interference term, followed by this term squared. And the types of experiments that we're building today are sensitive to the interference term. So that's the main idea. Okay? So this is how we think we're going to be able to measure CP violation. Now, there are lots and lots of problems along the way that have to do with the fact that we haven't measured these elements particularly well. And there might be degeneracies in the parameter space that you can compensate a CP violating effect. That's actually not true, but there's a different question about, you can also extract information about the CP violating phase just by measuring the entries very well. And that's a very different way of doing the same thing. Okay, so this is the way that we think we're going to measure this. And there's a whole list of experiments aiming at doing this. So I'll write them over here for no good reason. So right now, we're paying a lot of attention to the T to K ANOVA experiments. And then the next generation of experiments, which we're hoping to start building very, very soon. Actually, there's a groundbreaking for the Dune experiment today in South Dakota. So this is the Dune experiment. And then in Japan, there's the Hyper-K project. And both of these experiments are aiming at doing this measurement. And a lot of other stuff. But that's their sort of flagship measurement as well. Okay, so this is how we think we're going to see CP violation. One thing which I'll just mention in passing, because I don't want to spend too much time talking about this, is the other outstanding question that remains for neutrino oscillation experiments has to do with the mass ordering. And again, I mentioned this yesterday many times. The neutrino masses have to be ordered in some way. And I always want to emphasize that these are two different mass orderings. They're clearly physically distinguishable. If we knew what the masses were, we would not be confused by this question. It would be an obvious question. Because we only have access to the masses via neutrino oscillations, it becomes tricky to disentangle which one is which. There are two ways of doing this, and I'll just mention very quickly what those ways are. Oh, okay, that was weird. So I'll do it here, yeah. So there are two ways of doing this. One is, so I'll draw the mass orderings here. And this is called a 1, 2, 3. This is called a 1, 2, 3. And it's very easy to understand what the philosophy is. One very nice way of doing this is to appreciate the fact that if you stare at these two mass hierarchies, there's one fact that the neutrino oscillation experiments care about, which jumps out of these mass hierarchies, which is the following. When you're doing neutrino oscillations, even if you don't see, in many quotes, the interference terms, you can measure the delta m squares. And actually, there are 3 delta m squares. There are delta m squared 2, 1, delta m squared 3, 1, and delta m squared 3, 2. And they're all, there are only 2 independent ones. Nonetheless, in this hierarchy over here, the delta m squared 3, 1 is bigger than delta m squared 3, 2 in absolute value. In this picture here, it's the other way around. Delta m squared 3, 1 is different from delta m squared 3, 2 in absolute value. So if you can do an experiment that can tell whether delta m squared 3, 1 is bigger than delta m squared 3, 2, or the other way around, you can tell the mass hierarchy. There's a proposal there's an experiment that's being built right now to do this in China. It's called the Juno experiment. So the observable is still a nu e disappearance. So you're measuring nu e disappearance very, very precisely. And basically, you should be able to see the 3 different frequencies that are there. You know that they're related to one another, but the amplitudes associated to the different frequencies can tell 3, 1 from 3, 2. So in some sense, one way to picture this is you measure this oscillation spectrum, you take the Fourier transform, it has 3 frequencies in it, and in one hierarchy, the big frequency is has an amplitude that's larger than the smaller frequency, or the other way around. And because we know which one is supposed to be which, we can measure the hierarchy that way. The other way to measure the mass hierarchy, which is the one that we're more familiar with because we've been thinking about it longer, is the following fact. It turns out that the electron neutrino has a large probability of being measured as the neutrino number 1 or the neutrino number 2. And it has a really tiny probability of being measured as a neutrino number 3. So if you stare at these pictures, the electron neutrino is mostly here, or the electron neutrino is mostly here. So what happens is, when you include matter effects, the matter effects can tell whether the electron neutrino is mostly heavy or mostly light. And that's true even in a 2-flavor approximation. So that means if you can do experiments that have a lot of matter effects, they should be able to tell whether the electron neutrino is mostly heavy or mostly light, and then they can measure the mass hierarchy that way. And that's how the other experiments are hoping to look for this. In particular, the NOVA experiment is very sensitive to this, and the Dune experiment is super sensitive to this. So that's something to also keep in mind. So the last thing I want to say about this is that, so the matter effects are really good at distinguishing the mass hierarchy, but on the other hand, the matter effects make your life miserable if you're looking for CP violation. And the reason is that even if you have no CP violation at all, if the neutrinos are propagating through matter, neutrinos and antineutrinos will behave differently. No matter what's happening in the fundamental theory, that's easy to understand because remember, I told you that the matter potential is governed, the matter effects are governed by this matter potential, and neutrinos and antineutrinos have the opposite sign. One is positive, the other one is negative. This is easy to understand. It turns out that neutrino propagation through matter is actually CPT violating. And that's easy to understand because you're living in a background that's CPT violating. Again, if you turn your experiment from neutrinos to antineutrinos, the CPT conjugate of that should be neutrinos traveling through matter is the same as antineutrinos traveling through antimatter. We don't know how to do that experiment. So neutrinos traveling through matter and antineutrinos traveling through matter are qualitatively different things that you're trying to measure. So a lot of the work of these experiments goes into figuring out if they can separate out these matter-induced CP violating effects just from the fundamental CP violating effect. And you probably, yeah, go ahead.
You mentioned these experiments to try to measure whether the electron neutrino is mostly heavy or mostly light relative to what?
This is to determine which picture is correct.
But relative to what baseline?
Oh, relative to one another. So you have two sets of states, this state and that state. So you can tell if the electron neutrino is mostly here or mostly here. And here means heavy or light. So in the inverted hierarchy, the electron neutrino is mostly in the heavy state. And here the electron neutrino is mostly in the light state.
So are you contrasting to the mass of, say, a muon neutrino?
I'm contrasting this with regard to this mass. So that means I have an experiment that has a delta m squared. And the matter effects can tell whether, so you only measure the delta m squared and the amplitude, but you also get to ask whether the state that contains the most electron neutrinos is the heavy state or the light state. So I'm just measuring one relative to the other. And again, this probably sounded confusing, but that's the main idea. Okay? So any other questions? Yeah.
Is there any effort to over-constrain this matrix, like the lower?
Yeah. Oh, you mean if there's an effort to over-constrain this matrix?
Yeah, to over-constrain the given S.
Right. So that's what we would like to learn how to do. If you have a great idea, let me know. We have started doing this, by the way. We do this in sort of baby steps. So for example, I told you that there are two experiments that are sensitive to the solar delta m squared, the delta m squared 1, 2. This is the Kaplan experiment and the solar experiments. So you can do the exercise of, let's say that you didn't know that there was a third neutrino around. So you could do a two neutrino analysis of both of these experiments. And one of these experiments will measure the mixing angle, the other one will measure the mixing angle, and then we can compare if the mixing angles are the same. And if they're not the same, you will have discovered that your matrix is actually 3 by 3 and not 2 by 2. This is a hard experiment to do. We got a hint that this was actually true, but we cannot convince ourselves that we can measure theta 1,3 this way. So, for example, what's going on right now is that we have two very different ways of measuring theta 1,3. That's this small number there. One is with the reactor neutrino experiments. The other way is with this nu mu to nu e oscillations that I wrote down over here. So the idea is we have two very different types of experiments that are in principle measuring the same quantity. And you can compare the values that they get. And if those numbers disagreed, this would be a hint that you don't understand your matrix very well. If you want to do a more classic test of the unitarity of the matrix, then you have to start thinking about how you can measure taus. We do a very poor job of that, especially even in the planning of experiments. We're not there yet. Because the tau is required every time you want to do any check that has to do with a column of this matrix. The other check you can try to do is actually really hard. That would involve things like, say, the second row of the matrix. In order to do that, you have to see the muon neutrinos participating in the long wavelength oscillations. And we've never observed that very well either. So that's another very big challenge. And again, this is strongly related to this fact that in order to produce a muon, you need a high-energy neutrino beam. Again, if you have so if the wavelength associated to delta m squared 1, 3 is 1,000 kilometers, the wavelength associated to delta m squared 1, 2 is 10,000 kilometers, and again, you're stuck with the planet. So normally when we do these solar measurements, that's why we have to appeal to a nuclear reactor source, which is very low energy. So we give up on looking for the muon and tau neutrinos directly. We can only study the electron neutrinos, but then we have access to the long wavelength oscillation as well. And that oscillation for a typical reactor neutrino is about 100 kilometers. And 100 kilometers is okay. So any more questions about this? Okay, so very briefly I want to turn to topics number 2 and 3 in that list there. One is, of course, we've measured what the differences of the neutrino masses squared are. So you can ask yourself, what are the masses themselves? And the answer is we don't know, because neutrino oscillations cannot measure that. And we know that neutrino oscillations cannot ever measure that. That means you have to think about other kinds of experiments. So just for completeness, I want to mention very briefly the ways that we do that. The most powerful way that we have for constraining the neutrino masses is actually from cosmology. And you've heard a lot about different pieces of this story, and I don't want to repeat that at all, but the main idea is we are pretty sure that there are neutrinos left over from the Big Bang, even though we've never seen them before. And they've been around for a long time. You know, they were part of the radiation for as long as the photons were part of the radiation. Then they became less important when matter took over from radiation. But nonetheless, the neutrinos were there for the ride. And of course, today, the neutrinos are non-relativistic, so they are part of the cold dark matter even exactly today. And of course, they are part of dark matter that changes behavior from radiation to matter. So they go non-relativistic at some point, so they leave an imprint in structure formation and in other places as well. So by combining all of the cosmological data that we actually have an upper bound on the sum of the neutrino masses, which is of order 0.1 or 0.2 electron volts, depending on who you ask. There's a lot of uncertainty there. This is clearly a very indirect measurement, because as somebody, a friend of mine likes to say, no neutrinos are hurt in any of these measurements. So we only get to hurt all the other particles, and then we infer the neutrino properties from that. So this is a very, very stringent bound. The other bound that's very strong comes from kinematics. It's not as strong, but it's a nice measurement. Chris told you all about these types of experiments in the context of seeing the relic neutrinos. Of course, the way that you can, to back up one way, you can ask yourself, can we see a kinematical effect of a neutrino mass? So we can see the oscillations, which are this interference effect. But the question is, can we see the kinematics of the neutrino reveal to us that the neutrino has a non-zero mass? And the best way to look for this is in tritium beta decay, as far as we can do today. It's a very simple measure to talk about. I think Fermi was the one who first wrote this idea in paper. If somebody knows this is not true, let me know, but I think it's true. So the idea is you look at beta spectra, and you look at the very end of the beta spectrum. So here's your beta spectrum. It ends in some way, it doesn't matter how. And if the neutrino has a non-zero mass, you can ask the very naive question, which is, so the spectrum ends here, and the place where the spectrum ends cares about whether the neutrino has a non-zero mass or not. Because if the neutrino has a non-zero mass, you have to spend some energy to produce a neutrino. That means that the electron can't have as much energy as you thought it could. So this spectrum has a different shape. So it kind of looks like that. So the experiments that people are making, or the observable that they have, usually is to try to measure the shape of the endpoint of the spectrum, and the shape of the endpoint of the spectrum will reveal whether the neutrino mass is not zero or not. Whether the neutrino mass is zero or not. So that's the idea. There's this thing called the Catherine experiment that has been, they are building this for a while now, and they're supposed to start taking data soon. Sadly, this is kind of a time invariant statement, although for now it's actually true, it's going to be happening. They're turning on any day now, I'm told. So, but again, this is what they're trying to measure. The sensitivity that they have to the neutrino mass is of order 0.2 electron volts squared for the mass squared. And if you take the square root of that, that's way worse than the current cosmological bound. The nice thing is this is a really clean experiment that you can explain, you know, the gross features of the measurement to anybody that knows energy momentum conservation. So if they see something, we will be, I mean, as long as they can convince us that they know how to do the experiment, but we'll be very convinced that we know that the neutrino has a non-zero mass. That's much cleaner than, say, the cosmology measurement. Yeah?
What did they actually measure? The latest neutrino mass?
given the precision of the experiment right now, what they actually measure is a weighted average of the neutrino masses. They measure this thing that's incorrectly referred to as the electron neutrino mass. So let me define that. This is m beta squared. This is a weighted average of the neutrino masses. That looks like that. And you can convince yourself that that's what they actually measure. In reality, what they measure is much cooler than that. So what happens is this experiment is in a funny regime where the neutrinos are actually not oscillating, but the way that you describe neutrino oscillations is, or the way that you describe neutrino production is the following. You have a beta decay. You either get a neutrino number 1, or a neutrino number 2, or a neutrino number 3. Okay, so let's go with that. So if you produce, say, a neutrino number 1, let's say that this is the lightest one, then you get a spectrum that looks like this. If you produce a neutrino number 2, which is a little bit heavier, then you get a spectrum that looks like that. And then if you produce a neutrino number 3, which is heavier, just for the sake of argument, you would get a spectrum that looks like this. So this is what they measure. So this is the nu 1 spectrum, the nu 2 spectrum, and the nu 3 spectrum, and they measure a weighted sum of these 3 spectra. So actually the real spectrum is much cooler than what I drew. It has some features in it. The real spectrum would probably look something like, I don't know, let me draw over here. It would have some, it would look like that, which is really nice. Sadly, we have no hope of observing this at all. But this is what the real spectrum looks like. If you do it approximately, if you treat the neutrino masses as an approximation, it turns out that this is the object that you're sensitive to. Good. So any more questions about this? This is all I'm going to say about that. If you talk to Chris, he can tell you everything that there is to know about these types of experiments and much more. I hope. Or certainly much more than I can. How about that? Okay, so these are the two out of the 3 best ways we have of seeing a kinematical neutrino mass. I do want to emphasize this because it's important. Neutrino masses are very, 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 very small in particle physics units. And keep in mind, every time you do a neutrino experiment, you have to be involving the weak interactions in some way. So if you're producing a neutrino, you're probably in the nuclear physics and above regime. So you are in a world where typical energies are, on the best of all days, an MeV. And the neutrino mass is an electron volt. So this is 6 orders of magnitude smaller, except that kinematical effects go like the mass square. They don't go like the mass. So we're talking about a ridiculous effect. So observing a kinematical effect of a non-zero neutrino mass is very difficult, and we don't know another way of doing that. To be fair, you can try to use other beta decaying isotopes, and there are some attempts at doing that. There's one thing which I should mention is, so what's so special about tritium? Probably Chris told you about that before. And I'll say in an oversimplified way, what people tend to look for is they want this effect to be as visible as possible. And one way to do this is to get a spectrum that ends as early as possible, so that the end of the spectrum is not at the MeV range, but it's accidentally a lot smaller than that. So you want to pick an element that does that. So you say that the Q value has to be very small. Unfortunately, if you pick a Q value that's really small, that makes the lifetime of that isotope infinitely long, because the lifetime has something to do with the Q value. That means that there's no phase space for the decay to happen. That means that the lifetime is very long. So you want this to be small, but if it's too small, you don't get any events. So you kind of have to find some happy medium. And of course, you need some beta decaying isotope that you can actually go out and buy in the supermarket. You can't just have one of these impossible to find beta decaying things. Okay, so I probably said too many wrong things about this already. All right, so the next thing on the list is there's a very important question related to neutrinos. I also won't talk about this too much, but it's a very big question that we would really, really like to know the answer to. And in the context of a theory school, it's important to emphasize that if you want to try to understand how neutrino masses happen in nature, the zeroth order most important thing that you want to know is whether the neutrino is a Dirac fermion or a Majorana fermion. And the reason is if the neutrino is a Dirac fermion, the way that you pursue models of understanding where neutrino masses come from is very different from the way that you pursue models of understanding where the neutrino masses come from if the neutrinos happen to be Majorana fermions. So figuring out which one is the right answer is very important. So I will give you an abridged version of the discussion, but I do want to say a few things for people who are not absolute experts on what Majorana fermions are. And again, some of you probably know an infinite amount about what Majorana fermions are, and some of you have heard about it. So I want to give a quick and dirty explanation of what's the difference between a Dirac fermion and a Majorana fermion. And I think that the simplest way to think about this is to look at the number of degrees of freedom that you need in order to describe a fermion. Okay? And I like to go, and so just humor me for a second. So there's a very simple way of counting the number of degrees of freedom, for example, of the electron. So let's pretend that we know nothing about the electron, but we started doing experiments. And in particular, let's say that we're doing experiments one day and we discover a new particle. It's a lepton, it's a particle, it has negative charge. And we also measure its helicity, and it happens to be left-handed. So I've discovered that there's a particle, it has spin 1/2, it has charge, and it's a left-handed helicity particle. So with this information alone, I can predict the existence of another particle. Okay, and that particle is the same as this one, except that it has positive charge and it has the opposite helicity. Okay? And this is a consequence of the CPT theorem. If you ever observe the left-handed electron, then you can infer just from the CPT theorem that the right-handed that the right-handed positron must exist. If you keep on doing experiments, at some point, you might discover that the electron actually has a mass. If you discover that, then by taking advantage of this piece of information that told you that the electron has spin 1/2, then you know that there's another degree of freedom that also exists, and that's a right-handed electron. And that's because you know that the electron has a mass. There are lots of ways of convincing yourself of that. The simplest way is to go to the electron rest frame, which it has because it has mass. And in the electron rest frame, you observe the electron would spin up, and you don't have to know anything else to conclude that you must also be able to observe electrons which spin down. And if you don't believe that, you can turn upside down, and all of a sudden the electron has spin down. And that's all you need to know. Yeah? It's a different degree of freedom. So again, and we know about this very well, just from atomic physics, right? When you learn about the hydrogen atom, you can fit 2 electrons in the 1s state. And that violates the Pauli principle, except for the fact that the electron has spin, and it has a spin up and a spin down. So there are 2 different objects there. So from that perspective, that counts as 2 different degrees of freedom. And of course, if the right-handed electron exists, the positron has the same story. There's a left-handed positron as well. Okay? So that means that the electron, which is a proper Dirac fermion, is described by 4 degrees of freedom. Now let's do the same story with the neutrino, because that one, the amount of information we have is actually of the type that I've described. So we know that left-handed neutrinos exist. And again, all of the neutrinos we've ever produced in a laboratory and have had the pleasure of measuring, they were all left-handed. So this implies that the right-handed antineutrino also exists. We've also been able to see lots of those. So we're very sure these 2 particles exist. And now we've discovered that the neutrino has mass. So now I go to the neutrino rest frame. Sure enough, there should be neutrinos would spin up, neutrinos would spin down. So there's some other object here. And this guy has a friend who I guess I would call this way. So now the question I'm allowed to ask is, are these 2 degrees of freedom different from those 2 degrees of freedom? Now, in the case of the electron, you would never confuse this guy from this guy because they have different charge. So they're clearly not the same degree of freedom. In the case of the neutrino, you're not that lucky because this guy and this guy have the same charge, which is no charge at all. So it is possible that this degree of freedom is the same as that one, and that this degree of freedom is the same as that one. Okay? Except that it's not required. It's possible, but it's not required. So the question we're really asking is, how many degrees of freedom does it take to describe a neutrino? Is it 2 or is it 4? If you think about it that way, this sounds like a very easy question to ask, because 2 and 4 are totally different numbers. You would never get confused. The reason this question is really hard to answer is that if the neutrino didn't have a mass, then there would be no connection between these states and those states. So whether or not these states exist or not has absolutely nothing to do with neutrino physics. For a massless particle, for the massless neutrino case, these 2 degrees of freedom here may or may not exist, and the world of particle physics could not care less. So if the neutrino mass is 0, you can't ask if the neutrino is Majorana or Dirac. The same would have been true of the electron, by the way. If the electron mass had been 0, the left-handed electron would have been a particle. We would have called it a left-handed electron. And the right-handed electron would have been this other particle that would have absolutely nothing to do with the electron. We would give it some other name. It would be, I don't know, Bob. So, Bob and the electron would be totally different particles if the electron didn't have a mass. The only reason that they are the same particles is because the electron has a mass, and they are, in some sense, what we say the Lorentz partners of one another, because by a Lorentz transformation, one can turn into the other. And because this question can only be asked if the neutrino mass is not 0, so again, this is a philosophically important point. So you can only answer the question as to whether the neutrino is Majorana or Dirac if the neutrino mass is not 0. So that means if you can construct an experiment that can tell you the answer, you can't get an answer if the neutrino mass is 0, because you're not allowed to ask the question to begin with. What this means is that your answer has to die when the neutrino mass goes to 0. That makes the processes that can look for this really rare, because they all have to vanish when the neutrino mass goes to 0. So the rate for all of these processes that can answer this question are proportional to the neutrino mass itself. Okay, and that's why these things are so difficult to do. Yeah?
So you said we only ever measured left-handed neutrinos.
Correct.
So we would be measuring the helicity, right?
That statement is always about the helicity. That's correct.
But because I thought you only have left-handed chirality, but then if we know we have a mass, we could potentially also have a right-handed helicity state.
That's correct. So everything that you've just said is correct. So the question that we're asking is, if I have a left-handed chirality field that's producing a neutrino, the way that we describe it, it would produce the vast majority of the time in any experiment that you can come up with this state here. And because the neutrino has a mass, at a very tiny fraction of the time, it would produce a right-handed helicity state. So the question we're asking is, if I do that experiment, this right-handed helicity state, is it going to behave like this object, or is it going to behave like this object? And again, this is a very non-trivial question, because again, for the electron, you would have no doubt whatsoever that if you produce an electron out of the left-handed chirality field, you would definitely get a bunch of these guys, but you would get a small percentage of these guys. you would never ever get that guy because that would violate conservation of charge. So with the neutrino, we can ask whether you can do this funny phenomenon, which is to produce the other thing. Okay, so I hope we didn't fail the fire drill, but that's possible. Yeah, you're going to say something, yeah.
So we see the electron and bond, who's underneath of it, they're just totally different.
If the electron mass is exactly 0.
Okay, right, if they're not. And then you find Lorentz transformation.
Oh, if the electron mass is not 0, then you find that they're related by a Lorentz transformation.
Okay, so if I had a massless electron, and like say I wanted to put it into a doublet of some new SU2, suppose I was doing some model building, could I do that?
You could do whatever you want. You could do that.
But without violating the CPT or Lorentz.
That's correct, yeah. And I will say, and again, this is something everybody should appreciate, but this is exactly how the standard model works. In the standard model, all fermions are massless. And they're all different. You know, the left-handed electron field and the right-handed electron field have different quantum numbers. They can't even talk to each other if they wanted to. They need help. So that's what the Higgs mechanism does. It takes all of these particles, which are completely different particles. You know, before you break electroweak symmetry, the lepton doublet and the lepton singlet are totally different things. Again, they have different quantum numbers. You would not imagine that they could be related to each other in any way, shape, or form. They are only related because they have this Yukawa interaction with the Higgs, and the Higgs happens to have a vacuum expectation value. So in the vacuum of the world, these two things combine into a Dirac fermion. So that's how the standard model is designed. It's designed to take advantage of this fact that when you have massless fermions, you can write down a pure chiral theory. And the reason we like to do that is because nature told us that's how the universe works. So it happens to be that the weak interactions are chiral. So you have to construct all of your fermions out of chiral fermions. So we have to appeal to this Higgs mechanism to make sure that everything behaves as if they had a mass. So that's the short story there. But again, it's also true for the quarks. The quark doublet is an SU2 doublet. It's called a doublet. And then the quark singlets have different quantum numbers. They're also different things. You know, the left-handed up quark has nothing to do with the right-handed up quark until you turn on the Higgs mechanism. So it's not a surprise that this is true here. The only surprise is that the neutrinos could have a mass of their own without appealing to a partner. I guess the last thing which I'll say about this is, nonetheless, even if the neutrinos are Majorana fermion, we still speak about the neutrino and the anti-neutrino. And you also hear the statement that if the neutrinos are Majorana fermion, it is its own antiparticle. And that statement is correct, but nonetheless, you can still talk about the neutrino and the antineutrino because of the helicity states, in quotes. So again, every time you're in the laboratory and you produce a left-handed neutrino, you're going to call it a neutrino. Every time you produce a right-handed thing, you're going to call it an antineutrino. And that's the names that we've grown accustomed to. And we like them, so we don't not use them. Okay? This is true, for example, when you're looking for CP violation in neutrino oscillations. You could have asked yourself, if a neutrino is its own antiparticle, how do you look for CP violation? The answer is you do it in just the same way that I described before, because in one case, your neutrino propagator is mostly of the left-handed type, so you call that the neutrino. In the other case, it's mostly of the right-handed type, so you call that the antineutrino, and everything that we said before applies just as well. It's just that we're using the language in a slightly different way. So finally, how do we figure out if this is true or not? There are lots of ways of trying to do that. One is, as somebody asked in the back, if I produce a neutrino beam, it'll have a small contamination of the wrong helicity in it. So I can ask whether that contamination with the wrong helicity will behave like the antineutrino normally does, or is it going to behave like some object that doesn't interact with anybody? That experiment is impossibly hard to do, unfortunately. So the way that we look for whether neutrinos Majorana or Dirac is we remember that there's one way in which you can distinguish a neutrino from an antineutrino that has nothing to do with the helicity. By the way, the helicity is very confusing because the helicity of a massive particle is reference frame dependent. So it's kind of a nightmare to think about helicity if you think about it too hard. If you don't think about it too hard, it works out really well. But there's another way of telling the neutrino from the antineutrino, which is it appears as if this thing that we call the neutrino has lepton number +1, and this thing that we call the antineutrino has lepton number -1. So if lepton number is a symmetry of nature, then the neutrino cannot be a Majorana fermion, because the neutrino and the antineutrino carry a different charge. So they would be more like the electron, and with the electron, we're very, very sure the electron is not a Majorana fermion. So the way that we test for whether the neutrino could be a Majorana fermion is to look for physics processes that violate lepton number. So that's the best way that we have of doing this. Other than the thing that Chris talked about, if we could measure the cosmic neutrino background, whether the neutrinos are Majorana Dirac might give you a factor of 2 difference between what you expect to see in your detector. Factors of 2 are nice because they're big. So we hope that we have that under control, and we hope that we actually get to measure the relic neutrinos, and we hope that we get to see enough of them that we can tell 5 per year from 10 per year. So when we get there, we'll know. But until we get there, we have another way of looking for a lepton number violation. And the best bound that, the best hope that we have for this thing is to look for a nuclear physics process called neutrinoless double beta decay. So I'll tell you about this very briefly in about 5 minutes or so. So let me use this one, I guess. Okay, this one was here to begin with. So the idea is people have identified a very rare nuclear physics process. And the idea for this is pretty simple to understand. When you look at these tables of, what are they called? These nuclei that have different numbers of neutrons and protons but happen to have the same mass number, or whatever that's called. The same A. I don't remember what they're called. But if you look for nuclei like that, these are nuclei that can undergo beta decay, right? So if there's a nucleus here in some energy table, and then there's another nucleus here with a lower energy, then I can change a neutron into a proton, and then I can jump from here to here, and then I can emit an electron and an antineutrino. And there are some rare nuclei that also undergo beta plus decay that you might remember. So sometimes these families look like this. So if you live here, you can convert a proton into a neutron and emit a positron. And that's the beta plus beta decay, and that happens. It's been observed. And one thing that people figured out is that sometimes this pattern gets corrupted. So it turns out that there's some nuclei that are very tightly bound, and they distort the spectrum. So let's say that you have a scenario like this, where this guy would like to undergo beta decay into this one, but it can't because this one happens to have a higher energy. Usually the reason for that is that this guy turns out to be very tightly bound. So you have these doubly magic nuclei and things like that. But this guy notices that there's another guy all the way out here, so he could go into this one if they could do 2 beta decays at once. So instead of having 1 neutron convert into a proton, 2 neutrons can decide to convert into protons at the same time. And if you do that, that's called a double beta decay. So it's a process where a nucleus turns into another nucleus, emitting 2 electrons and 2 antineutrinos. So that's the process that you're looking for. Actually, that's not what you're looking for, but this is the phenomenon that happens. This was computed, I think, in the 40s or the 50s, and it's been observed. It's called a double beta decay. It's a ridiculously long lifetime. These are among the longest lifetimes we've ever observed in any physics process ever. They're like 10 to the 27 years or some ridiculous numbers like that. And in terms of Feynman diagrams, this process is, nuclear physics happens, W boson comes out, and then it goes to, let's do it the other way, electron, UE bar, and then it goes into electron, UE bar. So this is what's happening here. And of course, there's nothing spectacular about this process other than the fact that the lifetime is really long. So what you look for is something called a neutrino-less double beta decay. It's exactly the same process where no neutrinos come out at the other end. So it's a process that looks for this. And no neutrinos come out. And the reason this is exciting is because this violates lepton number by 2 units. Because there's no lepton number here. Z, by the way, is a nucleus, not the Z boson. But you have some nucleus here, goes to another nucleus, and you emit 2 electrons, so you violate lepton number by 2 units. And we've never been able to see that, but that's what people look for. Now, this is a very, very rare process that's never been observed, of course, and may be impossible to observe. Experimentally, it's relatively simple to spell out what's required in order to observe this. Your biggest enemy, of course, is the neutrino full double beta decay. This one here. So you see that in this process here, you have this 4 leptons in the final state. So for example, if you measure the energy of the electrons that come out, they have to be, the total available energy has to be shared with the neutrinos. Here the electrons carry all of the energy that's available to them. So basically here the electrons come out with some kind of a spectrum, and here the electrons accumulate at the end point of that spectrum. So that's how you try to do the experiment very briefly. Yeah? So I will try to draw that right now. And the short answer is we don't know because you need some new physics for that. The simplest Feynman diagram you can draw is exactly like this one, except that you do this. So this is the Feynman diagram. If you're more careful, we like to draw these helicity arrows like this. So the electron is a left-handed chirality state. So if we draw it this way, then this is a vector current. It goes this way. So it actually looks like this, if you know what this means. So this is a neutrino exchange between 2 W's. So if you want to remove all of the information that comes from nuclear physics, what you're looking for is WW to electron-electron via neutrino exchange. You can quickly convince yourself that this makes no sense unless the neutrino is its own antiparticle, because this propagator here does not exist if the neutrino is a Dirac fermion. It only exists if the neutrino is a Majorana fermion. Okay, and there are lots of ways of picturing what's going on here. One way is to look at the flow of lepton number. For example, here, you've produced, if you start here, you've produced an electron. So this thing here is an antineutrino. So you have an antineutrino coming in over here, and the antineutrino doesn't know how to produce an electron unless lepton number has been violated. So that's another way of thinking about that. There are lots of ways of thinking about that. Another way of thinking about this is that what you're really doing is you're producing 2 antineutrinos, and they're colliding and annihilating into vacuum. That also violates lepton number by 2 units because 2 particles cannot annihilate into vacuum unless they are a particle-antiparticle pair. So anyway, so this is the story here. The last thing I want to say about this is that when you calculate this, because of a mass insertion here, the amplitude for this process is actually proportional to a weighted sum of the neutrino masses themselves, where Q squared is the momentum transfer that you care about for this process. And as I tried to advertise before, if the neutrino masses were 0, then the rate for this should be 0. So that's why the amplitude is proportional to the neutrino mass. So the last thing I'll say about this is there's one extra wrinkle in this story, which is the object that shows up here is one element of the mixing matrix multiplied by another element of the mixing matrix. When we do neutrino oscillations, we normally get an element of the mixing matrix multiplied by the complex conjugate of an element of the mixing matrix. So The structure of these lepton number violating operators is, amplitudes is a little bit different. And what happens is that they're proportional to what are called the neutrino Majorana phases. It turns out if you do the counting of degrees of freedom in the mixing matrix and you assume that the neutrino is a Majorana fermion, there are a couple of new CP odd parameters that you can't turn off. They are physical, they're observable. But they only exist if the neutrino is a Majorana fermion. I don't want to go into this, but I invite you to think about that. The easiest way to understand this is when you're counting the number of physical parameters in the mixing matrix, for example, in the quark sector, the way that you normally do that is that you start out with a 3x3 unitary matrix, and then you perform field redefinitions to remove parameters. So you probably remember that story. Now, if the neutrino is a Majorana fermion, there are fewer fields around. Because remember, it has fewer degrees of freedom. So that means that there are fewer field redefinitions you can make in order to get rid of parameters in the mixing matrix. And that leaves you with 2 extra parameters that you can choose as phases. And it turns out that those phases only show up in phenomena where lepton number is violated. Okay? That's actually a non-trivial statement, and it has to be qualified. But that's the bottom line for that. So there are 2 extra CP violating phenomena, 2 extra CP violating parameters that only show up in phenomena where lepton number is violated. And we know that this is true because if the neutrino were a Dirac fermion, those parameters wouldn't exist, so you should not be able to measure them if they don't exist. So that's kind of the story there. Okay, so this, yeah. Yes, absolutely. And people have calculated whether you can see the Majorana nature of the neutrino by looking for E minus to WW. It absolutely makes sense. You are not competitive with double beta decay. Now, you wanna, this is important. So why do we do double beta decay? Because nuclear physics is way better at getting to very rare processes than collider experiments ever can. And the way that you want to picture this is luminosity. If you're doing a collider experiment, you're always trying to make things hit each other. And if it doesn't work, you have to do it again. And that takes a long time. It's really hard. If you want to do the nuclear physics experiment, you just get a lot of stuff, and you wait a really long time. You can't beat that, basically, to 0th order. It's the same, say, with looking for baryon number violation. If you want to look for baryon number violation, you can do it at a collider. You can do a PP to W+, for example. That's allowed. That would be really hard to measure. But on the other hand, you can also look for proton decay, which is the same story. You get a lot of protons. Those are easy to find. You put them somewhere, and then you wait a really long time. And hopefully one of those will do something. Or a neutrino will come in and hit something, but that's a different story. So yeah, so we spend a lot of time asking ourselves whether there are other ways to look for lepton number violation. And of course, it's fair to say that this process here is very biased towards electron flavor. So there are circumstances where the rate for this could be 0 because of flavor physics, not because of lepton number conservation. So if that turns out to be the case, we're going to need some other physics process that's not electron dominated in order to ask for whether lepton number is conserved or not. The challenge is to get something competitive. And we don't know exactly how to do that. But there are lots of ideas in the market. You can look for some rare meson decays. So you can look for something like K minus to pi plus, mu minus, mu minus. That's a lepton number violating decay. You can bet people definitely look for this, and you can also bet that they've never seen it before. And the branching ratio for this is less than, 10 minus 8 or something like that. It's small, but it doesn't compete with double beta decay. So any other questions? Yeah.
Yeah, I was going to ask in that direction, how could we disentangle, because we have 2 CP violating phases. If we measure the neutrinos double beta decay, we only have one combination of those, right? So we will need same kind of
Correct.
like that one.
So if you'd like to measure both phases and not some combined effect of them, you need more observables. People have speculated about this. One way of speculating is that you can do the experiment with different nuclei, and maybe that carries some information. This is an approximate expression. You can do a little bit better. That's totally hopeless, by the way, but that's a logical possibility. And then you have to appeal to other sources of lepton number violation as well. So yeah, but even seeing a CP violating effect here is virtually impossible. If you want to try to, there's a lot of work to be done if we actually think that there's hope of measuring these things. So any other questions? Okay, so the last thing I want to talk about is how do we get neutrinos en masse? Now, the main thing is to understand that that's a really important question. And because I won't have a lot of time, there are roughly, very roughly speaking, people look at the neutrino mass problem as they fall into two very different categories. And again, we all know this. In the standard model, masses are hard to come by. They have to be generated dynamically somehow. And for some reason that we don't understand, the Higgs mechanism works. So when we talk about giving neutrinos a non-zero mass, the thing that makes this field exciting is the fact that we have choices. With all of the charged fermions, we also have a lot of choices, but the Higgs mechanism choice looked like the right choice. The standard way that you learn in the textbooks. With the neutrinos, you actually have some choices. And the first thing you want to appreciate is the fact that if you look at the standard model particle content and you ask what's the neutrino mass, the answer is it's 0. And this is actually a very robust prediction of the model. Again, you look at the particle content, you look at the interactions, you write down the most generally normalizable Lagrangian. The neutrino masses are 0 to all orders in perturbation theory. So it's a great prediction, and it's wrong. Okay, so you need something different. So you have to add new degrees of freedom to the model in some way in order to give the neutrinos a non-zero mass. So there are two different avenues to pursue, which are different manifestations of adding new degrees of freedom. One is that you can add some new propagating degrees of freedom into your theory, and then you ask whether they give the neutrinos a non-zero mass. The other one is you add very heavy new degrees of freedom, which is equivalent to saying, let's start adding effective operators to the Lagrangian. So that's a way of accounting for very heavy degrees of freedom that you can integrate out. So the second avenue is the one that we like, because that's kind of how we think about physics beyond the standard model. We say we've measured everything at some energy scale. We imagine that there's some new degrees of freedom at a higher energy scale. We're not doing measurements at that energy scale. They're going to manifest themselves at our energy scale via effective operators. So then you can do the exercise, which was first done in a paper by Weinberg in 1979, of taking the standard model and just start writing effective operators that are consistent with gauge invariance. What's really exciting, and I'm sure most of you know in this room, is that there's only one operator that's dimension 5. That's this operator. You take a lepton doublet, you combine it with a Higgs doublet. That's a gauge invariant thing. It's not Lorentz invariant, so you can't write it in the Lagrangian, but you can square it. And this is a dimension 5 operator, so I write it out like that. And then you can convince yourself this is the only dimension 5 operator you can write down. All the other operators are dimension 6 or higher. So that's interesting. You can then ask yourself, if this scale lambda is very high, what does this operator do at low energies? And at low energies, after you break electroweak symmetry, this looks like a v squared over lambda, neutrino, neutrino. And this is a neutrino Majorana mass. This is very interesting because I didn't do very much. I just said, imagine the Standard Model is an effective theory. It's replaced by some other theory at some scale lambda. That theory manifests itself via effective operators. I can order the effective operators by their mass scale. It stands to reason that the lower dimensional operators are more important than the higher dimensional ones. There's only one that's dimension 5. And the only observable consequence of this operator is that the neutrinos have a non-zero Majorana mass. It gets better because all of the fermion masses in the Standard Model are proportional to V, and I'm predicting that the neutrino masses are proportional to V squared over lambda. What this is telling me is that not only do I predict that the neutrino masses are not zero, but I predict that they're qualitatively different from the charged fermion masses. They're actually very small if this effective scale lambda happens to be much bigger than the weak scale. And again, all of this is in Weinberg's paper in 1979. So you can say that he predicted that neutrino masses are not small. That neutrino masses are not zero, neutrinos are Majorana fermions, and neutrino masses are very small. All of this happens to be true. So if you ask around, 9 out of 10 theorists will tell you that this is how neutrinos get a non-zero mass. Because the circumstantial evidence is pretty strong. Except, of course, it could be completely wrong. Yep. Because these are the same field. They're not a left-right field or an LC kind of field. Yeah. So this is in a language where the L's are fermions, if that helps. So this is what Weinberg has predicted, and this is what everybody thinks is going on. So the physics question as far as building models, if you believe this is how nature works, is to ask yourself, what's the ultraviolet theory that gives me that effective operator? And a lot of effort is put into figuring out what's the ultraviolet theory that lives there. And of course, we're very good at building models that do this. So the real challenge is not to figure out what's the right model, but it's to start asking yourself, which one is the right model? So the cute part of appreciating how this operator gets realized is to start asking questions like, so if this ultraviolet theory is correct, then what else should I be able to observe? Okay, so that's the idea there. And I do want to discuss one example very concretely, and then I'll say something about Dirac masses as well. Okay. So the example I want to discuss is the one that everybody's very familiar with, but I'll hopefully present it in an interesting way. So let's say we want to give neutrinos a non-zero mass, and but we want to write a renormalizable Lagrangian. Oh, and by the way, I should have said this. If you plug in numbers into the thing that's behind that board, which I didn't do correctly, then the scale that you need for the new physics is about 10 to the 14 GeV. It's a very high scale. And I'll come back to this in just a minute. So the simplest model I can write down is I can take the Standard Model and I can add a new field, and I'm going to add a new fermion, and I'll make that new fermion not be charged under the Standard Model gauge interactions, and I'll call that the left-handed anti-neutrino field. And that, again, is a fermion. That's my model. And then the next step is once you have a model, you write down the most general Lagrangian that you can that's consistent with the gauge symmetries of the model. So I have a Lagrangian that looks like the Standard Model Lagrangian plus some kinetic energy term for this new C field that I wrote down. And then you appreciate the fact that this guy can marry this LH combination with some Yukawa coupling. And finally, you remember that this guy is a gauge singlet, so it's actually allowed to have a Majorana mass. that looks like this. Okay? And I put a factor of 2 here because I wanted to find this mass properly. So again, if you don't do anything, so that's the most general Lagrangian that you get. After electroweak symmetry breaking, this really simple Lagrangian, and again, let's pretend that there's only one neutrino in the world so that life is better. So there's only one family here. So this type of, actually, we can do that, yeah. So this type of Lagrangian predicts that there are neutrinos. There are actually 2 of them, and they're all Majorana fermions, and they all have mass. And that's easy to see. After electroweak symmetry breaking, this term looks like this. This is times V. This is what we call a Dirac mass. And in this language of biofermions, again, if you're not familiar with that, a Dirac mass is any mass that combines 2 fermions that are not the same fermion. So these are 2 different fermions, so this is a Dirac mass. And this is a Majorana mass because it combines 2 fermions that are the same fermion. So if I write down the mass matrix for this guy, there are 2 of them. This mass matrix looks like this. And this is in the basis of a nu and nu C. So this is a great model because it tells me that there are neutrinos. That's good. They have non-zero masses. It's actually too good because it tells me that there are twice as many neutrinos as I needed to begin with. But that's fine. I mean, I can definitely live with that. So now, if we're doing good phenomenology, the last question we need to ask is, what are the parameters of my Lagrangian that explain the non-zero neutrino masses? And the answer is there are lots and lots of parameters that work. And I want to discuss 2 limits very briefly. One limit is, let me write this over here. And just give me 5 more minutes and then I'll be done with that. I can ask what happens if m is equal to 0. If m is equal to 0, this matrix looks like this. This is what's characteristic of a Dirac fermion. So in this scenario, the neutrino is a Dirac fermion, and the observed neutrino mass is lambda v. This is a really nice model, because if I set this mass here to 0, then this Lagrangian has an extra symmetry in it called lepton number. Lepton number is exact. My neutrinos are Dirac fermions, and their masses go like lambda v. And if I want to fit the data, I have to pick this number lambda to be about 10 to the minus 12. Now, there's nothing wrong with 10 to the minus 12. You should remind yourself that the electron-Yukawa coupling is about 10 to the minus 6. So you've been living with this all your life. So 10 to the minus 12 and 10 to the minus 6 are just as bad. End of story. The other possibility is that this number m is not 0, and it's much, much bigger than lambda v. In this case, I have to diagonalize this matrix to calculate the mass eigenstates. And one mass eigenvalue is m. The other mass eigenvalue is lambda v squared over m. This one here is mostly nu c, and this is mostly nu, because the matrix is mostly diagonal. So in this scenario, if this mass m is much, much bigger than these Dirac masses, you have this interesting phenomenon that what we call the neutrino mass, this is a standard model neutrino, is a really, really light. So even if this lambda v is of order the weak scale, by making m large, I can make this neutrino very small. This is one manifestation of what's called the seesaw mechanism. And this is a really important result because it says that if I couple the neutrinos to a hidden sector that has a new mass scale in it, I can explain why the neutrino masses are very small, because the neutrino masses are inversely proportional to this new mass scale that I've put into my theory. Again, everybody likes this idea. And of course, in this model, all that I'm doing is realizing the Weinberg operator, this LH squared over lambda, in a way where the scale of the Weinberg operator just happens to be or 1 over lambda, is a lambda v squared over m. Okay? So this is a way of realizing that dimension 5 operator, which I talked about before. Now, this is a 2 out of 4 possible hypotheses that I could have come up with. There are 2 more. One is that m could have been a lot smaller than lambda v. This is a funny scenario where this matrix is almost completely off diagonal. That's what's called a regime where the neutrinos are a pseudo-Dirac fermion. And that's completely allowed by the data. You need lambdas to be very small. They're still 10 to the minus 12, but you can't rule that hypothesis out. So the last model is when m is of order lambda v. That's when this matrix here is sort of some generic matrix and no approximations are good approximations. And in that scenario is actually ruled out by experiment. It's ruled out by experiment because this is a scenario where you have neutrinos and you have this other object here that looks like a stereoneutrino. And those stereoneutrinos mix a lot with the standard model neutrinos. That's ruled out by experiment. So finally, the last thing which I'll say, because I've run out of time, is this is a great model because it also tells you what the challenges are for giving neutrinos a non-zero mass. Because let's say that somebody told you, like an angel or something like that this is the right model. So you're very, very sure, you bet your house that this is what's going on here. So the neutrinos are getting a mass this way. You can still ask yourself, what is this number m, capital M? It's some new scale in the theory, and you have absolutely no idea what that number is. Theoretically, you have no guidance whatsoever. So just by staring at the Lagrangian, you have no right to tell me what that number m is, because that number is sort of a protected number. If that number were 0, then the Lagrangian would have an enhanced symmetry in it. That means that that number is Toft natural. I don't know what the nomenclature is. It's technically natural to have any value at once because it's a symmetry breaking parameter. Worst of all, if you look at the neutrino masses, this is the neutrino mass, and you can ask yourself, for what values of m and lambda do I get a good fit to the data? And the answer is the following. If you make a plot, so I make a number line here, this is for m. And then you can ask yourself, for what value of capital M do I get the right neutrino masses, and I get a result that's consistent with all of observations that I've ever made to date? It turns out there's an upper bound. The upper bound is when the theory becomes strongly coupled. So if this coupling here gets too big, then the theory is no longer valid in the region of mass space that you want the theory to be valid, very roughly speaking. So there's an upper bound around 10 to the 15 GeV. Then you can ask yourself, is there any lower bound? Remember, I don't want to be in the regime where these two masses are comparable, so I have to stay away from that. But the lower bound is around here at around 1 electron volt. So this entire parameter space is allowed, which is interesting. If you're very picky and you believe in cosmology, which some of you do, then KeV is kind of a concern. Maybe 10 keV is a little bit safer. So maybe this is, you have trouble with cosmology here. If you go below 1 electron volt, then you get in trouble with neutrino oscillation data because you start seeing these stereoneutrinos. And it's fun to ask, when do you get out of trouble? And the answer is you get out of trouble around, I think, 10 to minus 9 electron volts. So if you live here, the model is ruled out. If you live here, everything is totally fine. The neutrinos are Majorana fermions, but it's impossible to tell by doing an experiment. They behave as if they were Dirac fermions, and they just want to annoy you a little bit by having a small violation of lepton number. So again, it's a really simple model. I don't have to think very hard to write this down. And the parameter space for this is gigantic. And this is one of many, many models that realize in this regime over here the Weinberg operator. Okay, so since I did run out of time, I wanted to make one statement about Dirac neutrinos. Dirac neutrinos are nice because the Lagrangian has an enhanced symmetry, this thing called lepton number. I do want to emphasize that this is qualitatively different from the standard model. And again, this is a little bit of propaganda, but I'll talk about it anyway. You've appreciated the fact, and and this came up I think when Nima was talking or somebody else was talking, is that in the standard model, lepton number and baryon number are symmetries. They're global symmetries of the model, but they're also accidental symmetries. Nobody asked for that. It just happened. Okay, this is important. If you add a right-handed neutrino to your theory, that's no longer true. You add a right-handed neutrino, and then you have to pause and ask yourself, what about this term? Why isn't this term there? It's allowed by the gauge symmetries. It's a relevant operator. So if it's not there, it has to not be there for a reason. So if you believe in Dirac neutrinos, then lepton number is not an accidental symmetry. It's a proper global symmetry. It's there. You have to put it in by hand. Otherwise, you would have been doing a seesaw mechanism whether you liked it or not. So this means if you buy into the fact that the neutrinos are Dirac, then you've just learned that the ultraviolet physics, whatever it is, really likes lepton number. It does not violate lepton number. If you are worried about the fact that lepton number is anomalous, you can repeat everything I just said with just a B minus L. So again, if neutrinos are Dirac fermions, lepton number is a fundamental symmetry of nature. That is not true in the standard model. In the standard model, lepton number was an accidental symmetry that happened, and we have no right to believe that the ultraviolet theory has to preserve lepton number. So if the neutrinos are Dirac, it's a big deal. The disadvantage, and the reason people don't believe that the neutrinos are Dirac, is because the neutrino masses are very small. And one thing which I didn't say is that also the neutrino masses are not just very small, they look different. They are qualitatively small relative to all of the charged fermion masses. If you stare at the masses, they stand out. So that's why people buy into this Majorana neutrino thing. So one very, very simple idea of explaining why the neutrino masses are small and somehow the neutrinos are still Dirac fermions is to make a very simple observation. And this is the last thing I'll say, and then I'll stop. So the way that we form a neutrino Majorana Dirac mass is by taking this object here. This is this gauge singlet thing that I can form out of standard model fields. This is also called the neutrino portal. And then I want to marry this with the right-handed neutrino. This is my neutrino Dirac mass. Now I know that the neutrino mass is really small. So let's say that the reason the neutrino mass is really small is because it's actually forbidden. And it's easy to make this mass forbidden by saying that the right-handed neutrino has some other quantum number I didn't know about. So imagine the right-handed neutrino has some other quantum number that I didn't know about that's not shared by these guys. So that would make this coupling here forbidden. Now, of course, that means the neutrino masses are zero, so I'm not any better off than I was before. But imagine that the right-handed neutrino is part of some other hidden sector where it's also a massless fermion, but it can marry its own Higgs boson, like that, in such a way that this thing here is also a gauge singlet of the hidden sector. So now, this is a gauge singlet, this is a gauge singlet, this is a fermion, this is a fermion. I can combine them now. This is an allowed operator in my Lagrangian now, except that it's a higher dimensional operator. That means that it's a consequence of some new UV physics I've never heard about. But lo and behold, I can write this out. And now the neutrinos get a Dirac mass that's also very small. It kind of looks like V times V phi over lambda, where V phi is the symmetry breaking sector in the symmetry breaking scale of the hidden sector, and lambda is some unknown UV physics. So this is an intriguing idea that people first came up with in the context of mirror world models. But it does say that maybe the reason the neutrino masses are small is because the right-handed neutrinos are a member of some hidden sector that is charged under that hidden sector, and that's why they're prevented from marrying the neutrinos. They can only marry the neutrinos at some higher dimensional operator level. And maybe for some reason that we don't understand, the UV physics preserves lepton number once you assign lepton number to the hidden sector as well. And that would be a good way of giving very small Dirac neutrino masses. And again, I've been spending a lot of time thinking about this. That's why I'm talking about it here. But it's an interesting idea where you generate a very small Dirac mass that looks a lot like the small Dirac mass that you get out of the seesaw mechanism. It's also a dimension 5 operator, but it gives you a very small Dirac mass instead of a very small Majorana mass. And again, I did not do this topic justice. People spend a lot of time building neutrino mass models. And the main reason is the following. I wrote this out here. Even though this model has this gigantic parameter space, it's really hard to test. Because over here, you have this light right-handed neutrino state where you would hope you should be able to see it in an experiment, except that the theory is really weakly coupled here. Here, the theory is not very weakly coupled. It's actually strongly coupled, but you have this new state that weighs 10 to the 10 GeV. So you're not going to see it in the laboratory here. So one thing that people do is to ask themselves, can I generate a model that violates lepton number, gives the neutrinos a non-zero mass in a way that you actually can test the theory in the laboratory? This sounds like weird model building. I mean, why would you want to build a model because it can be tested in experiment? And I hope the answer is obvious. It's because it can be tested in experiment. But these are not the prettiest models of all. But nonetheless, they do emphasize and they allow you to identify all the different ways in which you can test the neutrino mass models. And most of them have nothing to do with neutrino physics. There are things like the G-2 experiment or the searches for lepton flavor violation that provide a lot of information about other models that also generate, for example, this kind of operator, except that they are testable in the laboratory. So anyway, I think I'll stop here. Thanks.